So let's talk about the basics for the series solution method. The basics for series solution method. Series solution method. So some people call this a power series method. So it's the same thing. Power series method. Power series. So what we're going to do, let's talk about some related material, and then in a different video we're going to solve the problem. So this is just the basics what we need to solve a problem in series method. So power series. So what's a power series? A series of the form let's say sigma. I'm going to use the index n for that. So n goes from 0 to infinity. These are what we normally call infinite series. It's going to go up to infinity. Other ones what we call finite series, like normally important in computer science and engineering, things like that. But this is general case, so you could go to infinity. It's called infinite series. So there are some coefficient we call Cn, and then x minus a. So a is a center. So it's called center, and the index n goes there. So this is what we normally call a power series. And if you expand, so what are you going to get when you plug in n equals 0? We assume that when you plug n equals 0, x minus a to the 0 is 1. That's the assumption. So we do that, and then so we write c naught, and then when you plug in n equal 1, you're going to get c1. X minus a to the 1, we don't write 1, and then c2, x minus a to the 2, like that. So that's what we call a power series, center at a. So that's a center. So this is what we call a center. Okay, so a is a center. At a, so it's very important. Center at a. Power series center at a. So it's called a power series. Power series. So it's clear like why we call it power series, because it's a series and there are some powers of x minus a to the n. Good. So let's look at some examples. So the first one, how about this one? So let's say sigma n going from 0 to infinity. I mean, you don't have to start with 0 always. We can do it any way you like, because what we call reindexing, that we can discuss later. So to the x to the n, 2 to the n xn. So if you look at few terms, what do you get? If you plug in n equal 0, so you're going to get 2 to the 0, x to the 0, that means 1, plus then when you plug in n equal 1, you're going to get 2x, and then so it's like 2 1 x1, but is 2x, and then we're gonna get 2 to the 2 x squared, like that. So if you look at just gonna continue like that. Actually, let's not write like that, so I'm gonna take this part out. So like that, and then so this if you simplify a little bit, you're gonna get 1 plus 2x plus 4x squared, like that. So that's the power series. So it's we can say it's a power series. So is a power series you can say centered at what? You don't see anything. That means because a equals 0, so that's why centered at a equal 0. Okay, it's important. Centered at a equal 0. So let's look at one more. How about this one? So let's say sigma n going from 0 to actually you don't need 0. Let's put something else here. So let's say you're going to start with 3. So 3 to infinity. Let's say you have some negative n, that's going to change the sign. 1 over 3n x minus 1 to the n. It's like that. So what are the first few terms that you get? So if you plug in n equal 0 as before, and you can see that again you get negative 1 to the 0, 3 to the 0, x minus the 0, so you get 1. And when you plug in, actually you can plug in 0, we have to plug in n equal 3 because that's the starting value. So let's plug in n equal 3. If you plug in n equal 3, what do you get? Let's start it. Negative 1 to the third power 1 over 3 to the third power x minus 1 to the third power, and then plus negative 1 to the fourth power 1 over 3 to the fourth power x minus 1 to the fourth power, like that. So if you write first few terms, negative 1 to the third power means negative, 1 over 3 to the third power means 27. This is x minus 1 to the cube, we leave it like that. X negative 1 to the fourth power means 1, so it's positive, we don't write anything. So and then 3 to the fourth power means 81. You get x minus 1 to the fourth power, like that. So you can see this is a power series centered at 1. So it's a power series. It's a power series. It's a power series centered at a equal 1. So and then you can see, actually we can discuss that later. You can see here we start with n equal 3. The question is, can you write this so that this can start with n equal 1? Actually we can do that, but that's we gonna discuss later, how we can reindex this one, and that's very important for the power series method. But that we can discuss later, how to reindex this one so that this can start with start at n equal. So so my goal is this: find an index, so that you can rewrite this one so that you can start with k equals 0 rather than 3, and then some coefficient that you need to find, and x minus 1 in this case, and also some index here. So it might not be k, because if you put k, then you can see that k equals 0, that doesn't match. So you can see that this has to be, if you want to start with k equals 0, so this has to be k plus 3. So it's clear, because when you put k plus 3, you can see when you plug in n equals 0, you're gonna get x minus 1 to the 3. So that's exactly match with that. So that's what we need, but we can discuss that later. Okay, that's at the end of this discussion. Good. That's called reindexing technique. So let's talk a few other things. So we need to talk about what we call the convergence. So what's a convergence? So I'm going to call facts. So you can learn more about this one if you review the power series major lecture from Calc 2. So so what's a convergence? So let's say convergence. So if the series sigma n going from 0 to infinity, we just put n equals 0, just a customary thing, but it can be anything, any positive integer or even negative integers. So you can see when you plug in, like if you look at this one, this is just a function of x, right? It's just a function of x. So the whole thing is a function of x. So it's very clear. Now what we can do, so this is just a series. If you look at this one, you're going to get every time a term. And then remember in Calc 2 we discussed how to check whether a series converge. So we talk about like about 7-8 different techniques. So we can use any of those techniques to test whether the series converge. That means you get a finite number, because there are infinitely many terms here. You add infinitely many terms, but the question is whether it's going to go to infinity or whether you get a finite number. So if you get a finite number, I mean sometimes it can go to infinity, sometimes can go to negative infinity, sometimes it's going to fluctuate between two numbers or many numbers, or what can happen, sometimes you gonna get a one number, a finite number. So that case we call it is converge. In that case you get a finite number, we call it converge. Okay, so in other words, also say if this exists. See, exist means converge. So it exists. Exists we say the series converge. We say the series converge. Converges. The series converges. So if we find a number, we call it converges. And then there are a few other things. So in the convergence case, we can talk about interval of convergence. Interval of convergence. I don't think that's a good color. Interval of convergence. Interval of convergence. So we have the convergence. I think it's like a different color. So convergence. And then what we call the interval of convergence. So what's the interval of convergence? So interval of convergence. So this what we normally do is the set of all points, set of all x, you can say set of all x at which the series converge. The series converges. And then later, actually you remember that there are three cases, and then in those cases you can see that it's always an interval. Okay, it can be like a single dot or point, what we call singleton, or a finite interval or infinite interval. So like that. So but it's always an interval. Okay, so it's important. So let's say always an interval. Always an interval. We can discuss that later. And then what we call the radius of convergence. The radius of convergence. Radius of convergence. The radius of convergence. So what's the radius of convergence? When you write the interval form, you can find how far it is from the center. So that's what we call the radius of convergence. The radius of convergence, the radius of the interval, the radius of the interval, the radius of the interval, the radius of the interval is called the radius of convergence. And so if you draw it, and you can see, so that's the interval, and then so you can, so it's A, and it's gonna go in two different directions. So this is so this gap is what we call R, that's the radius, how far you go from the center. So it's gonna go both directions. And then this is A plus R, this is A minus R, so it's going to go in two different directions. So actually this radius is just the half of the length. So you can see if you just take the half of this, so R is simply you take the total and it's just the half of that. So R is the half of the length, the total length. Good. So as we discussed before, there are three cases. Let's talk about those three cases. Three cases. So there are only three cases. That's also very interesting. So what are the three cases? So the first one, convergence at A only. That's the first case. Converges at A only. Because it is always converges at A. So the converges at A only. In that case, what's going to happen? In that case, R is simply 0. It doesn't go anywhere. So R is 0. And the second one, so actually in this case, if it's only converges at A, R is 0. So that means you can see what's going to happen now. So it is x minus A, the gap is 0. So in that case, you can see that it's x equal A only. So it converges at A only, because that's the only solution you have. Just one solution. And look at the second case. In the second case, what's going to happen? Converges on an interval. Converges on an interval. That's like most common case. In that case, what's going to happen? You're going to find some positive R, so that it's going to converge in x minus A less than R. So you can see geometrically what does that mean? This means you start with A, go R in the two direction. So that's very clear in the figure, in the line, number line we draw there. So that means that so x is in between two numbers. What two numbers? It can be A plus R, or it can be A minus R. It's in between those two, and that's the interval you're going to get. So it's going to create an interval, or you can simply write this one as A minus R to A plus R. That's the interval talking about. But there is still something that you need to consider, because we don't know what's going to happen at the corners. So those two corners we have to check separately, because it may or may not converge as the corners. Okay, so may or may not converge. May or may not converge. May or may not converge. Good. So that's the situation we get, but we're going to look at an example to see. We have done a lot of examples. If you look at the main power series lecture, there we discussed several cases how we can do. And the last one is, you can see there are some functions it can converges everywhere. So converges everywhere. Converges everywhere. Converges everywhere. So if converges everywhere, it's very important, everywhere. So it means that R is infinity. R is simply infinity. So if you look at the interval again, it is x minus A less than infinity. Infinity is not a finite number. This means that it pretty much covers everything. R is infinity. So x is all real numbers. So x is any real number. So it's very important, any real number, any. So that's the third case. So at the corners, we want to check, we want to make sure that, so we normally check whether it's going to converge or not, but we cannot say anything in general for that case. So those are the only three cases. So there are no more than that. There are only three cases. So those are the only three cases we need to consider, that for any power series, it's going to converge at A only. It's going to converge in an interval, and then for some R, and we can discuss how to find that R. R is what we call the radius of convergence, and we can discuss how to find it. And then converges everywhere. In that case, R is infinity. So again, and the corners, when in the second case, in the corners, we need to check whether it's going to converge at those corners. Sometimes it works, sometimes it doesn't. So let's see how to find the radius of convergence. That's the next one. So let's discuss how to. So how to find the interval of convergence. How to find the interval of convergence. Interval of convergence. For that we use the ratio test. So we can use the ratio test. That's a common practice for that. So it's a ratio test. So let's say, so what's a ratio test? So suppose Cn not equal to 0 because we are dividing by that. In the series sigma Cn x minus an, we normally do not mention the index. Let's call this is an, this whole term called an. Now what we can do, let the limit when n goes to infinity, an plus 1 over an. We're going to look at this limit, but this you can simplify it a little bit. It's the limit. If you substitute, you're going to get, what are you going to get? You get Cn plus 1 x minus an plus 1 over Cn x minus an absolute value. Now you can see, you can simplify this a little bit. This n terms get cancelled, so you only get one of them, but you can pull out that one. So if you pull out that, so you're going to get x minus a absolute value because it is under absolute value, and then you're going to get the limit n goes to infinity. It is simply Cn plus 1 over Cn absolute value. So whatever you get, the whole thing that you get, we're going to call this entire thing, we're going to call this is L. So we're going to call this is L. So this L going to decide what's going to happen to the series. So there are three cases, as you remember. So what's the first case? If this L is less than 1, then we know that the series converge absolutely. So the series converges absolutely. So this in turn implies that the series converge, because we know that if a series converges absolutely, it converges. So the series converges. So you can even directly say that. So we have more information. So it converges absolutely. In other words, it means that the series converge. So that's the first case. If L less than 1, series converge. If L greater than 1, what's going to happen? The series diverge. The series diverges. That's the second case. So if L greater than 1, diverge. You don't have to do anything after that. We stop there. Now the question is, if what's going to happen if L is exactly equal to 1? That happens sometimes. For example, if you look at the harmonic series, is L equal 1. And then if you look at, for example, sigma n squared, L again equals to 1. So it's like that. And then if you see 1 over n squared, which is also in L equal to 1, but some of those series converge, some of them diverge. So there is a problem. So if L equal 1, we normally call the test fail or the inconclusive. So inconclusive. So inconclusive, that means you have to use some other test. So that means a series may converge or diverge. So in that case, we had to use some other test. So what we normally do is use other test. So that's why sometimes we call the test fail. The test can fail. And then, so the note is, we're going to use this to find the interval of convergence. So we use this. We use this to find the interval of convergence. Interval of convergence. Good. So now let's actually do an example and see how things gonna work. So let's say an example. Just pick like some basic series. So find the interval and the radius of convergence of find the interval and radius of convergence. Find the interval and radius of convergence of, let's say, sigma n going from 1 to infinity x minus 3 to the nth power divided by 2n times n, something like that. So as before, we can use the ratio test. So by the ratio test, so what we're going to do, we're going to look at the limit. We can look at the limit when n goes to infinity, a n plus 1 over a n. A n means the nth term. So we look at the ratio. So this is the limit. N goes to infinity, sigma. So let's plug in n plus 1 first. So it is n minus 3 to the n plus 1 over 2 to the n plus 1 and n plus 1. And then similarly, n, but it's 1 over. That means you write the terms upside down. So this is 2 to the n goes to the top, n, and in the bottom it is x minus 3 to the nth power. And you can see there are a lot of cancellation going on. This n and n can cancel, and then also the same thing happen with this n and that n also cancels, and that's it. You cannot cancel anything else. So let's write whatever we have now. So you can see this simply you're gonna get the limit n goes to infinity. You're gonna get 1 of x minus 3, and then 2n get cancelled, so you get 1/2 left because 2 is in the bottom, and then also you have n over n plus 1. Now we can split the limit with each of them. 1/2 and x minus 3 does not depend on n, so that means you can pull out that. So that means you're going to get 1/2 x minus 3. It comes with the absolute sign because it's inside the absolute sign. And then you have simply the limit n goes to infinity, n over n plus 1. And you can see that the limit of n over n plus 1 is simply 1. So this is equal to 1. So if this is equal to 1, you simply end up getting 1/2 x minus 3. Now according to the ratio test, you know that if this limit is less than 1, so we can set this. If this is less than 1, so it's coming from the so we set this value. It's coming from the ratio test. We know that if this limit is less than 1, the series is going to converge. So we can set it like that and solve for x. So that's the whole point. So we set it like that and then we're going to solve. So that means what we have is 1/2 x minus 3 less than 1. Now we can simplify. This is like not that difficult. So you can see you can multiply by 2. So that means you can write this one as x minus 3 less than 2. And if you write this in interval form, what does that mean? You can go 2 away from 3 because that's a center. That's a center. So you're going to go 3. If you're going to go 2 units from the center, so that means you have, what do you have? You have, if you go to the left side, it is 3 minus 2 x. If you go to the right side, it is 3 plus 2. So this implies that this is 1 and 5. So that's going to give you the interval. So that if you write the interval notation, this is between this is from 1 to 5, the open interval. So so that means, and and also this is the radius of convergence. So that's the radius of convergence, so which is 2, and the center is 3. That's the center, that is 3, radius is 2. A radius always get, once you write this form, that's where you're gonna get the radius. So you have to write this form, to find the radius. So from here you're gonna get the radius. So radius is 2. Okay, perfect. Now what do you want to know? We know that at between 1 and 5 a series converge, but we don't know what's going to happen in the end. So let's test that. So let's talk about. So the radius of convergence. So the radius of convergence is r equal to find the interval of convergence, of convergence, we need to test the endpoint. We need to test the endpoint. So we can test the endpoints. So let's do that. So we can see at x equal 1, what we do, we're going to go back to the original series and plug in that value. So you can see this is 1 minus 3 to the n over 2 to the n times n. So if you simplify this a little bit, you can see from the top you're going to get negative 2 to the n, so that you can write as negative n 2 to the n over 2 to the n, and you can see these two get cancelled. So you're going to simply get sigma n going from 1 to infinity, negative 1 n over n, and you can see this going to converge by the alternating series test. So converges by the alternating series test. We know it called AST. Good. Let's do the same thing with the other point. So let's look at the other corner. So at x equal 5, the series n going from 1 to infinity. So we do the same thing. It is 5 minus 3 to the n over 2n. You can see this also simplifies nicely. So you're going to get n going from 1 to infinity. The top is 2n now. So it's simply 1 over n. We know that this is the harmonic series, diverges because this is a p series with p equal 1. P series with p equal 1. We know that the p greater than p less than or equal 1 is going to diverge. So p series with p less than or equal to 1. So that means diverge. So the series diverge at x equal 5. That means interval of convergence is only going from 1 to 5, including 1. So the interval of convergence is from including 1 up to 5 without 5. So that's the interval of convergence. Radius of convergence is 5. Okay? So the radius of convergence is 5. Is r equal to the interval of convergence is 1 to 5. Good. So if we have several converging series, you can do a lot of things. You can add. So what we write algebra of converging series. Algebra of converging series. So if you know that there are two series which can converge, you can do like nice things. You can add them, you can multiply, um, so you can add two series, you can multiply. Okay, before that, you can subtract. So you can subtract, and then you can multiply, and divide even, and also you can like raise the powers, but we multiplication with the raised to powers. And then also that's one set of things that you can add, subtract, multiply, divide. And then also you can take derivatives, you can differentiate and integrate. So you can differentiate, and integrate. You can differentiate and integrate converging series. So that's going to be useful for us when we do the power series method. So this is exactly what we do. We can assume a power series solution and we can integrate. We can take the derivative of that. So that's important for us. And then the one of the fact that you may remember, it does not change the interval of convergence. No, it does not change the radius of convergence, but it may change the interval of convergence. So when you do that, it does not change. It does not change the radius of convergence, but may change interval of convergence, because the problem is the endpoints. Maybe you have to add endpoints or you have to remove the endpoints. It may change interval of convergence. That's like a fact that we know. Good. Okay, those are the major things that we need to kind of recall about them. So let's look at several common power series. So these are some of the common Maclaurin series or power series that we use in most of the engineering and science studies. So you may see some nice patterns here. For example, if you look at the exponential function, you can see exponential function, sine and cosine function. You can see they all converge everywhere. And also if you look at the hyperbolic sine and cosine function, you can see that they all also converge everywhere. So those are like kind of common functions that are very useful, and interestingly they converge everywhere. So that makes our life much easier. And also one other thing, if you look at the exponential function, you can see it has like pretty much all the powers. And then if you look at the cosine function, it's only even powers, so that's the even powers. And if you look at the sine function, that's odd powers. So what you do, you look at the exponential function and pick the even powers, and you alternatively change the sign, and then you're going to get the cosine function, and you pick the odd powers and alternatively change the sign, and you're going to get the sine function. And one other thing that you notice is if you remove the sine condition, you can see you end up getting the hyperbolic function. For example, if you remove the sine term of the cosine, you end up getting the hyperbolic cosine. And then if you remove the sine term of the sine function, you end up getting the hyperbolic sine function. So those are some kind of relations that you that may help you to remember them. So the cosine functions all even powers, sine function has all odd powers, cosine start with 1 and alternatively change the even powers, sine start with x and alternatively change the odd powers. And if you look at if you remove the sine term, you're gonna get the hyperbolic sine and cosine functions, and all converge everywhere. That's something that you learn. And also you can see there's another relation between the sine and the tan inverse. The major relation is you simply remove the factorial term. So you can see if you remove the factorial term, you're gonna end up getting the tan inverse. See, there's no factorial term here. So that's the only difference. So if you remove the factorial term, sine becomes tan inverse. But there is a major difference now. You can see the interval of convergence change now. Interval of convergence reduced to -1 to 1. And also there are two other things that are important. For example, the bottom one are the geometric series. If you look at geometric series, you know that is a 1 over 1 minus x you can write as 1 plus x squared plus x cubed, like that. That's simply n going from 0 to infinity, x to the n. And you know that that's only going to converge from -1 to 1. So this is what is this? This is simply x less than 1, centered at 0. So at 0 you can only go 1 each way. So radius is 1. Interval you can see it doesn't include 1 or -1 because they're going to fluctuate. One is diverge, the other one fluctuate. And the other important one is the ln 1 plus x. If you look at ln 1 plus x, and you can see it's only converted from -1 to 1, but 1 you can, but not the -1. So yeah, so these are like kind of common power series that may help you in most of the calculations. Okay, good. So let's continue. So let's do just one example and let's see how things gonna work. Some kind of algebra here. So algebra of power series, or arithmetic of power series. So let's say algebra of power series. Algebra of a power series. So let's do let's say simplify. How about sin x plus cos x? Let's see how it works. So we're going to do substitute for sin. We know that this is all the odd powers without sign change. Without sign change. Like that. And then if you look at the cos, that's the even powers without sign change. So so the multiplication is the addition. So plus 1 plus x squared factorial 2 x to the 4th factorial 4, like that. And if you add them, you can see you have everything, all the powers. It's 1 plus x squared over 2 factorial plus x 3 over 3 factorial, like that. But what is this? This is simply e to the x. That's an interesting result. If you add the two, cos x plus sin x, it is ex. Let's do one more. How about this one? Let's say let's try to find a power series of a product. So find a power series. Find a power series, a representation of e to the x sin x, e to the x sin x. So what we can do, we're gonna use the table and we're gonna substitute for them. So that means e to the x sin x. So let's substitute for each. What are the e to the x? Let's try the first few terms. It is 1 plus x squared over factorial 2 plus x 3 over factorial 3 plus, like that, times, so it's a multiplication, x minus x squared over 2 factorial plus x 4 over 4 factorial, like that. Now what we can do, let's look at the first few terms. So let's start with the smallest term. What's the smallest term? When you multiply the first term with first term, you get x as the first term. And then what else you get? What's the next one? You can see that x get x squared, and then you're gonna get 1. So the next one would be x squared minus 1/2 x squared, and then keep doing, and then you're gonna see that the next one would be 1/2 minus 1/6 x to the cube, and then the next one would be 1/6 minus 1/6 x to the 4th. Well, like that. Those are the first few terms, and you can see they simplifies, and then you end up getting x plus x squared plus 1/3 x cube, like that. So that is a power series representation of ex sin x. Yeah. So these are the kind of things that you can do. So you can pretty much pick two power series and substitute and find the first few terms. This is like useful, like especially if you want to find a limit problem. This is gonna be very helpful in those kind of situations, because you see that the x is common here. For example, if I ask you what is the limit of, so I'm going to show you something like really quickly. If you say what is the limit, let's say the limit of when x goes to 0, I'm going to say ex sin x minus x squared over, let's say, x cube. So if I ask a problem like that, and you can see from this expansion, and you can see if you bring x minus x, if you bring x and x squared to the other side, you simply get 1/3 x cube. So if you divide by x cube, you know that each term has either x3 or more powers. So when you plug in x equals 0, you simply end up getting 1/3. So the answer is 1/3. So you can do like really amazing things like that. But just imagine if you just need to find the limit of this one, just use some other techniques, it can be like really difficult. But if you know this technique, you can get some answer really quickly. Okay, so those kind of things are in a different video. You can watch them if you're interested in. Okay, good. So those are a few things that are important. So let's continue. Let's see what other things that we need for our power series technique. So we're gonna look at things like this. So let's look at some of the definitions that are important. So this is a definition. So let's see. So what we mean by an analytic function. So analytic function. Analytic function. So this is like important topic that we need. So so the definition of a analytic function is, so we say a function f is said to be analytic, is said to be analytic, when you say analytic, you have to say at what point. Analytic at A, if it can be written as a power series, if it can be written as a power series, in x minus a. I mean, if you can write up as a power series, that will be enough, but in exactly x minus a. So if you can write a function as a power series in x minus a, we call it is analytic at a. Okay, so it's important. So it's to be analytic at A. Okay, analytic at A, then it can be analytic at A if it has a power series in x minus A. So we can say there is fx equal sigma n going from 0 to infinity, so we use 0. So some coefficients and then x minus a to the nth power. So if you can write it like that, so we call it is a analytic function. So any analytic function you can write it in this form. So that's the important part. If you're analytic, you can write in this form. Good. So let's look at some examples. So let's say you have a function fx equal 1 over 1 minus x. So you can say this is analytic at x it's analytic at a equals 0. Okay, it's analytic at a equals 0 since, what's the reason? Can you write this as a power series in x minus 0, that means x? Yes, so you can see that the reason is fx, which is 1 over 1 minus x, which is equals to 1 plus x squared, like that. That's the geometric series. So this you can write as sigma n going from 0 to infinity x to the n when x less than 1 for some radius of convergence. So it doesn't matter, but if so there has to be some kind of radius convergence, but you can write this function as a power series. Okay, so that's the idea. And what are the functions? So there are a few common functions. So you can see I'm going to write this as a note. So polynomials are the exponential function and the cosine functions are analytic. At any point. It's very important. At any point. At any point. That's the important part. It's analytic everywhere. Also like sin and cos also. And then also, what about the rational functions? The rational function is analytic. Rational function is analytic at any point x where so you can say where qx not equal to 0. So what is the qx? So let's say your rational function is, you can write it like px over qx. So you only worry about the bottom function. So so what you do, if you can write a rational function means the quotient of two polynomials. So if you remove all the points where the bottom function is 0, it is analytic at all the other points. So that's what you remember. You only look at the bottom function, check where it is not equal to 0, and it's going to be analytic at all those points. Good. So those are kind of common things that we need to know about when you talk about the power series solution method. And then let's talk about some other idea that's important. But for like in a general course like that, we normally focus on polynomials and rational functions. So, but there are other functions as well, but those can be complicated. But we focus on mainly about polynomials and rational functions. So So we say we focus on polynomials and rational functions. Good. We focus on polynomials and rational functions. Good. And then there's another one that's important, what we call the ordinary points and singular points. So when you look at a differential equation, there are special kind of points that we are gonna talk about. So let's talk about that now. Ordinary versus singular points. So let's look at it like common differential equations. Let's say consider let's say ax y double prime plus bx y prime plus cx y equals 0. I'm going to call this equation number 1 because this is very useful. We're going to refer to this again and again. Now what is say if you get a differential equation like that, what we normally do is we can divide by x. So divide by x, so once you do that, you're going to get a y double prime plus bx over x y prime plus cx over ax y equals 0. But you can see that you can do this only when the bottom function ax not equal to 0, because if there's a x where that's equal to 0, you cannot do that. So that's gonna create this that's gonna define what we call the ordinary and singular points. So that means and then also we're gonna write this like we normally call as before. We normally call this is px and this is qx. Okay, so let's define what we mean by a so you can say a point. That's the definition of ordinary point. Okay, so a point x equal x naught is said to be ordinary, is said to be an ordinary point. Said to be an ordinary point, is said to be an ordinary point of the differential equation 1 if both coefficient functions, if both bx over ax and cx over ax, if both bx over ax and cx are analytic at x naught, are analytic at x naught. So that's what we check. We check whether those two functions, because those are rational functions, two rational functions. So we can check whether those two functions are analytic. In other words, we check whether those two functions can be written as power series. So if you can write those two functions, the ratio functions, as power series, you call it is analytic. And then we call the point is ordinary point. Okay, analytic at x naught. So and then we say a point that is not analytic, that is not a point that is not analytic is called a singular point, is called is called a singular point. A singular point. It's called a singular point. So we have ordinary points, that means at which those two functions bx over ax and cx over is analytic, and we have singular points, that means at least one of them is not analytic. So that's kind of interesting. So let's look at several examples. So ordinary points. So let's look at this one. The first one, let's say y double prime plus y equals 0, and let's say y double prime plus 3y prime plus 2y equals 0. So you can see that the coefficient functions are constant. That means when you divide, that's just a constant. This is nice analytic function. So you can see the coefficient functions. Coefficients are constants. So they are analytic. They are analytic at any point. They are analytic at any point. They are analytic at any point. So any point is an ordinary point. So any point, that's very important. So any point is an ordinary point. So all the points are ordinary points for this. The next one. How about this one? Let's say we have y double prime plus ex, y prime plus, so let's say cosine x, y equal, so that's a cosine coefficient equals 0. And then again you can see these two functions, what we normally call the px and qx functions. Px and the qx functions. They both analytic functions that we know because they converge everywhere. So again the coefficient function. Coefficient functions are analytic. Analytic at any point, okay, at any point. So any point is an ordinary point. Okay, good. How about this one? So you can see y double prime minus ex, y prime plus ln x, y equals 0. How about this one? What about ln x? So if you look at ln x, and you can see that at 0 this function is not even defined. So there's a problem now. So let's say I'm going to assume that x positive here because it's ln x. So at 0 this function is not defined, because if it's a power series, then what you can do, you can see that it's a nice continuous function. But at x equals 0 it is not continuous. That means not analytic at 0. but analytic at everywhere else. Okay, so that means x equals 0 is not an ordinary point, it is a singular point. So you can say like this: ln x is not continuous at x equals 0, and it is not a it is not a analytic point. So it's not an analytic point. So that means which is a singular point. That is x equals 0 is a singular point. It's a singular point. Any other point, any other positive x is a ordinary point. Any other positive x is an ordinary point. Good. So those are the ordinary points. Let's do the same thing with singular points now. Let's learn a little bit more about singular points. So let's talk about singular points. Singular points. Let's look at this one. So D, we say x y double prime plus y prime plus x y equals 0. You can divide by x, and then you can write this one as y double prime plus 1 over x y prime plus y equals 0. So in this case you can see the two functions that we need to talk about. So in this case px function is simply 1 over x, and the qx function which is 1. So you can see that the px is not analytic at x equals 0, is not. It's not analytic at x equals 0, so it is a singular point. So it is a singular point. Good. So let's do one more before we kind of finish this discussion about these ordinary singular points. So how about this one? Let's look at a Cauchy-Euler type of equation: x squared minus 1 y double prime plus 2x y prime plus 6y equals 0. So let's look at like another way to look at that. So you can see that we're gonna, like, when you divide by the coefficient of the y double prime term, what's gonna happen? This term gonna go to the bottom of the rational function. That means we only need to worry about at what point this gonna make 0, because if you remove those points, and those are the singular points actually. So in another way, we can write it like this. So something that we can, so let's say not a number x equal x naught is an ordinary point, so it's an ordinary point of the differential equation 1 if a x naught, a means the coefficient function of the largest derivative term, not equal to 0. So that's the kind of test that we can do. We only need to worry about that one. Okay, this is the case, then we call it is an ordinary point. And x equal x naught is a singular point, is a singular point, if a x naught equals 0. So that's the kind of shortcut to find ordinary or singular points. So that means according to that argument, so in this case what's going to happen, singular points are the solutions of x squared minus 1 equal to 0, because that's the coefficient function, so we can set it equal to 0. This implies that x equal plus or minus 1. So those two are the two singular points. So all the other points are ordinary points. The other points are ordinary points. Other points are ordinary points. And then let's talk about this simple idea. So what we're going to do, there's a nice theorem which says that when this we can have those power series. So let's talk about that. Good. So what we call existence of power series. Okay, so the theorem. So existence of power series. Power series solutions. Existence of power series solutions. Again, consider the differential equation ax y double prime plus bx y prime plus cx y equals 0. That's what we try to do. So what it says that if x equal x naught is an ordinary point, of star, then we can say, because it's a second order, so then there are two linearly independent solutions, then there are two linearly independent solutions, there are two linearly independent, and there are two, that's very important, there are two linearly independent solutions, in the form of power series, in the form of power series, are centered at x naught. The form of power series centered at x equal x naught. So what it says that, so that's also important, centered at that point. So if you know that there is an ordinary point, then it says that there are two linearly independent solutions that can be given as power series solutions. So that means those solutions can be given as y equal n going from 0 to infinity, a constant x minus a, or in this case x naught, x minus x naught to the n. So you can say that you can find two solutions in this form. So which converges on some interval x minus x naught less than r. With r positive. So that's very interesting. So it says that if you know any ordinary point, it says that you can find series solutions. Okay, so we say such solutions are called series solutions. Okay, so that's the goal of in another lecture we're going to talk about how to find them, but this says that if you know any ordinary point, you can easily find those series solutions. And then before we finish, we're going to discuss one more idea. So that's what we call rearranging indexes. So let's talk about that, and then we can discuss how to kind of apply these ideas in a like when we solve problems. So rearranging indexes, that's very important. Reindexing power series. So reindexing power series. So we're going to use a method that I developed. I'm going to call it a seesaw method. So what's a seesaw method? So we're going to use this. Use to reindex. Sigma notations. So the idea is like this. So let's say there's a seesaw and there's a pivot, and there are two people riding here. So there's one person and the other one. So what's normally happen is, you know that one person go up, at the same time the other person go down, but the pivot doesn't have any change. It's gonna stay there, but it's still on one side go up, the other side go down, so that it's gonna pivot, it stays the same. So let's say this side can go up by 3 feet, then this side go down by 3 feet. So that's the idea. So we can use that fact here. For example, let's look at a problem like this. So let's say you have a sigma, let's say n going from 3 to infinity, 2 to the n plus 5 x minus 1 to the n, let's say minus 4, like that. So what we can do is, we're going to consider these two separately. We're going to consider the outer index, that's the outer one, and inner index separately. This is the inner index. So there's a n, these are all inner index. So what we're going to do, at any time you can increase one and you can decrease the other one. It doesn't matter which one, but you can increase one outside one, then you can decrease the inside one, so that the total gonna fix. So for example, you can write the same one. So these are all the same. So I'm going to say these are all the same. Okay, these are all the same. For example, like this. So you can write this one in many different ways. So let's say sigma n equal 3 to infinity 2 to the n plus 5 x minus 1 to the n minus 4. So let's say I'm going to increase this one by 3 unit. So if I increase this one by 3 unit, you can write this one as sigma n. Let's say I'm going to decrease by not increase. Let's do decrease. You can, but let's start with like that. So let's see, we're going to decrease this one by 3 unit. So if you decrease this one by 3 unit, what's going to happen? You can see your index now going to start with n equal 0. So since you decrease outside, you're going to increase inside. So that means this is 2, you're going to increase by 3. That means it's going to be n plus 8. X minus 1, you increase by 3. So that means this is n minus 1. So you decrease by 3. So that means you have to increase by 3. That's what happened. That's the first one. You decrease by 3 outside, you increase by 3 inside. So these are all the same. So if you expand, you're going to get exact same numbers every time. And let's do another one. How about you're going to decrease more? So let's say you're going to increase by 2. Let's say you're going to increase by 2. So if you increase by 2 here, outside index, then what's going to happen inside? Inside you have to decrease by 2. So that means your new one can be written as, so what you did, you increase by 2. That means n equal 5. And then you can decrease by 2. That means 2 to the n plus 3 x minus 1 n minus 6. And you can see that they are all the same, just a different representation. Okay, so you can write in any different way you like, because this reindexing going to be very useful when you try to solve some problems. So this is the kind of idea that we try to do. What I'm going to call it a seesaw method. Okay, seesaw method looks like a seesaw. One side go up, the other side go down. Good. So let's call it seesaw method. Seesaw method. Good. So let's see how we can use this in a problem. So this is a problem that we're trying to do. So let's say rewrite. So an example, rewrite as a single sum. Rewrite as a single sum. So for example, let's say you have these two sums, sigma n going from 2 to infinity n minus 1 cn x to the n minus 2 minus sigma n going from 0 to infinity cn x n plus 1, like that. So what do you want to do? You want to write this one as one series. No, this is going to add them. So rewrite as a single sum, okay, or single power series. Okay, what I'm asking, rewrite as one power series. Okay, write as one power series. Good. So what you're gonna do? You're gonna look at, like, what are how the indexes change. So you can see, for example, if you look at let's look at a few terms, and you can see when you plug in. So I'm gonna write it. So first write. So let's say we first write the terms that do not have a common power in x. We first write terms that do not have a common power in x. That do not have a common power in x. And then leave the ones with the common power within the sigmas. Leave the ones with a common power. Leave the ones with the common power within the sigma. Within sigmas. Okay, so that's the kind of first thing we do. We look at what terms are not gonna give the same powers. So for example, if you plug in n equal 1, x gonna be in the first one. So I'm gonna call these two are the 1 and 2. So this is the first series, and there's the second series. It's easy to refer. So, and you can see that in the first one, when you apply n equals 0, you get x to the 0. And if you plug in n equals 0, that's the first index, you can see that you're going to get x to the 1. So that means when you plug in n equals 2, you get x to the 0 power. That's the uncommon one. So what we're going to do, we're going to write that first. That's the first thing to do. So now how we do it. So we can write the two series again. So sigma n going from 2 to infinity, n minus 1 Cn x to the n minus 2 minus sigma n going from 0 to infinity Cn x to the n plus 1. So what we do, we write the uncommon one first. What is the uncommon one? When you plug in n equal 2, you get uncommon one from the first one. So let's write it. So when you plug n equal 2, that means you're going to get 2 n minus 1. So actually this is n equal 2. So let's write it 2. So it is 2 minus 1 c to the 2 x 2 minus 2. So that's the uncommon one. And after that, when you apply n equal 3, you get x to the 1, and when you apply n equal 2 in the other one, you also get x to the 1. So that means they're going to match. So we're going to write, when you start producing the common terms, we're going to write it. So you see that starting with the next index, so that means it is n equal 3 to infinity. So here what happened, this is n equal 2 case. This is n equal 2 case. So 2 case is not common. But when you apply n equal 3, you see that they are the common one. So here the inside nothing changes. You see n x to the n minus 2 and then minus sigma. So you have n going from 0 to infinity Cn xn plus 1. So you can see that in these two, now when you apply n equal 3 from the first one, you get x to the 1. When you apply n equal 0 from the second one, you also get x to the 1. So that means they are the common. So common one we leave. So now the goal is to rewrite using one index. So what we can do, we can rewrite these using one index. Okay. Rewrite as one series. So that we can do. So now for that we can use the seesaw method. So it's very easy. So I'm going to do this one down by 2, and inside I'm going to bring everything up by 2. All of wherever you see n, bring it up by 2. So up by 2, up by 2. Then you can start with 1. So then you can see when you up by 2, this is simply becomes x to the n. So do the same thing. So that means to get the x to the n, what we're going to do here, you want to bring this down by 1, and then you can see you need to bring up by 1. Okay? So it's easy. You just need to look at how to match the two indexes. Just think about this. So this is the one you need to think, how to match them. Okay, because this one go down by 1, this one go up, up. Okay, so if you do that, then what's going to happen? This simply becomes, so this equals to, you have 2 times 1 here, 2 times 1, C2, so x to the 0, so you don't see that. And then the other sigmas, what we did was, this down by 1, down by 2, so that means this can be n equal 1 to infinity, and inside you up by 2, that means n become n plus 2, just add 2, n minus 1 become n plus 1, Cn becomes Cn plus 2, and then x become x, n minus 2 become x to the n. That's the first term, minus the second term. So what's the second term? You bring it up by 1, that means it can be n equal 1 now, and then Cn, this can be Cn minus 1, and then this can be x, n plus 1 become, you subtract 1, so that means xn. So you can see that they nicely match the two index. So that's the whole point, just match the two index and see how many you want to bring up and down. From that you decide what you can do in the outside. Remember, like, you change everything inside. Okay, good. Now what we do, you can see that is xn and same index, so you just combine the two coefficients. So that's what's going to happen. So if you combine them now, so this simply become 2c2 plus sigma n going from 1 to infinity is the same index now. So you can see, it's the same index now, just the same n. So you can combine them. So we're going to pull them together. So you can write them as n plus 2, n plus 1, Cn plus 2 minus Cn minus 1. You're going to just get the coefficients and then x to the n. So a very simple idea as just one coefficient. See, just a single coefficient. So this is very useful when you try to solve problems using the power series technique. And then if you want to try, just write the first few terms. Okay, so write this for you to try whether that's the case. Write first few terms, and verify that it gives the same terms. It gives the same terms as the original series. Okay, that's an interesting idea. So we can use this method when finding power series solutions. Okay, I'm going to give you one to try. So rewrite as one sum. And you can even do this for like many, like not just 2 but 3. So let's do 3. So you can try this. So sigma So let's say n equal 3 to infinity, n minus 2 Cn x to the n minus 1 equal sigma minus sigma n equals 0 to infinity. We can say n Cn x to the n plus 2 plus, you can even multiply by a number if you want, but you can just a number. So let's say 3 times sigma n equal 2 to the infinity. We can say 2n Cn x to the, let's say, n minus 1. Okay, so see whether you can write this as a single sum. So what you want to do, just check the first few terms and write all the uncommon terms, and stop right after you start producing common indexes, common powers of x. When you start seeing common powers of x, you can stop, because you can combine all of them into one power series. So you can see the answer in the description.